All right. Okay, this is actually take two of me recording this, because apparently the first time when I recorded it, the audio is not working. Anyway, okay. So reactions at the alpha carbon, right? So we learned in previous chapters that we have not very many reactions that happen to alkanes, right? We get radical brominations, dibrominations, chlorinations, but those reactions take a lot of energy. And we just won't get a regular like acid-base type reaction, right? This will not happen. So the way that we can do this is we can add groups that serve as electron sinks, serve as methods to allow us to move around electrons and resonate between structures such that we have a compound that's actually a little bit more stable with having a negative on it, right? When we add the OH, we get a pK of 15, carbonyl O, pK of 5, ketones, stabilized by resonance. So pKa will vary based on the Y group, right? So pause right here and try to guess why the ketone has a higher pKa than the aldehyde. Okay. So weakly electron donating, no electron donation, right? So if we're donating into here, and this is supposed to be an electrophilic spot of attack, it's becoming less electrophilic, right? So the pKa is going to be higher. Cool. It's just basically more electron density. Okay, esters. Esters have a higher pKa. Pause the video and try to guess why. Okay. This is because of the fact that when we have a minus here, we have two systems, right? So we can delocalize on this side or we can delocalize on this side, right? But when the electrons are delocalizing on the left side, this negative is kind of just naked on this position, right? We can't delocalize into this system when we have this resonance structure, right? So because of that, it's basically a competing resonance of stabilization. It's a little bit higher than a ketone. Okay. For the same reason that we just talked about, this is not as good as this, but this is a really, really good resonance structure, and it's very characteristic of what you're going to see throughout this chapter. We can move this negative here up, we can move it here up. Two methods of resonance stabilization. Isn't that a lit picture? Okay, nitriles. Nitriles are SPKF 25. They're pretty good. Because of the fact that when we have the negative, we can come down here, kick this up, and we can delocalize electron density. A nitro group. So this is probably the best electron withdrawing group because negative can come here, kicks this up, and it has all kinds of resonance conjugation here. Cool. Very strong electron withdrawing group. Okay, so these are some of the pK values of an alpha carbon in various different compounds. And I think it's sufficient to understand the trends associated with these, but I wouldn't concern yourself too much with memorizing each of them and being very particularly hyper-specific about them. Okay, ketoenol tautomers. So a ketone heavily favors this side of the reaction. It goes between keto and enol. 99.9% of it is in this form. Only 0.01% is in this form. So maybe this is pretty dramatic, right? So pause the video and try to guess why this structure doesn't have as dramatic of a difference. Like you still see 85% to 15, but that's not, like as dramatic as 99.92.01. Okay, so the reason why we have this is because the enol form is stabilized by the hydrogen bond and the double bond conjugation. Cool. Phenols. So phenols are the only compound that I can think of where the enol form is actually favored. I guess any form where the enol introduces aromaticity into the structure, right? Because we know that aromatic compounds are really, really strong. Because we just, we talked about Frost diagrams last quarter and how we have energy that delocalizes across. And I think you can just generally understand that benzene is a very stable compound. So phenol stabilized by aromaticity. Cool. Tautomerization. So I feel like this is a reaction we've seen so many times, but we haven't really gone through a particular mechanism of it yet. There's two methods, base catalyzed and acid catalyzed. So base catalyzed, we deprotonate the H, comes down, kicks up, and right away, we get this form. Okay. Um, After that, protonation step, workup step, we have our enol. We need a really strong base here. Acid catalyzed, we can use a weak base because we're increasing the strength of the nucleophile. It's then also important to note that when you draw these intermediates, no negatives under acidic conditions. You never draw a negative on any intermediate or final structure under acidic conditions. No pluses under basic conditions. All right. So again, Basically what you would expect. Cool. Tautomerization. Basic conditions, acidic conditions. Um, yeah. Okay, cool. Halogenation of the alpha carbon of aldehydes and ketones. So there's two ways to do this, acid catalyzed, base catalyzed. It's important to note here that I can't think of a single scenario where when we can choose between acid and base catalyzed, we would ever choose base catalyzed. Acid catalyzed is almost always better for literally everything that you do. Just keep that in mind. But anyway, acid catalyzed forms the monosubstituted product. Pause the video here and try to guess why this is the case. You could also pause it after we look at the mechanism of acid catalyzed, because that also might give you some insight into why. Okay, so this is the mechanism for acid catalyzed halogenation. It's kind of what you expect. The catalysis is when we have a protonation at the carbonyl O, makes it really electrophilic, so we can attack this hydrogen and eliminate it. Even with a weak nucleophile, comes down, kicks up, comes back down, kicks off. It's also really important to note that when you draw this structure, you have to draw it with three arrows. Do not put a negative here, because I know that you might be thinking like, it's the same thing and like effectively like I get the same product. And if you go through that mind of thinking for like prediction, it's totally fine. But if you were asked to draw a reaction mechanism, you actually have to draw it out as this. Like you can't just draw it as a minus. Just keep that in mind. It's just one of those things, right? So finally, deprotonation step, we get our Br at the alpha position. So Br is inductively withdrawing electron density from the oxygen, which actually makes it less basic. So this oxygen, remember that it needs to protonate or it needs to grab a proton from here, which makes this an electrophilic site. When we install the Br there, it actually makes it less basic and unable to do this. Um, so that's why we only get a monohalogenated product. For base catalysis, all the alpha hydrogens are halogenated. Okay, so successive brominations will also occur faster. This is because this effect here that made the previous question like prevent this reaction because we're doing base catalysis, it's actually helping it, right? So what happens? We deprotonate right away. We come here, we kick up, comes down, Br, kick us off a Br. So this position here is really, really electrophilic, right? Because we're getting withdrawal this way and withdrawal this way, which means that this is a very acidic hydrogen. So we come here, we kick up, come back down, grab a Br, kick off a Br. Cool. Dibrominated, you know? If we had a H here, we would have a tribromination. Okay? Sick. So we'll keep on deprotonating until there's no more protons. Okay, HVZ. This is the Hell-Vollard-Zelinsky reaction. This reaction becomes pretty important when you talk in 109C about amino acids, specifically in biochemistry, and just, higher level organic chemistry biology courses. Okay, so halogenation of the alpha carbon. What's going on here? So we start with a carbon, or just start with a carbon, sorry, carboxylic acid. What am I saying? This first reagent, I think it's sufficient to understand that it'll reduce an OH into a Br. I don't think you're on the hook for the mechanism for that. So I wouldn't worry too much about that. We'll get a tautomerization step of converting this double bond here into a double bond here. Um, the electrons would come down, they'll grab a Br, kick off a Br. Cool. So now we have a Br. This is called an ipso position. It's directly attached to the C here. Just fun fact. Anyway, a Br is directly attached to the carbonyl carbon, and it's also attached to alpha. H2O, so, as we would expect in an acyl chloride, this is a really good leaving group, so this should come here, kick off, deprotonate. Or actually, I don't know if it needs to deprotonate. It does need to deprotonate, sorry. Deprotonates this installed species. The Lewin pairs come down, they kick this off, and we're left with this compound. Cool. Nothing new here. Just like using reagents that we've seen in the past for a different purpose. Okay, replacing the alpha halogen of the carbonyl compound. So only use a poor nucleophile. Strong bases will favor elimination, which is why we have to use a poor nucleophile here. The nucleophile should be strong enough for SN2 because SN1 will form unstable intermediates. So, reasonable nucleophile. Something like an alcohol or an H2O is okay. Like, don't use a ridiculously weak nucleophile, but, water is always a safe bet. Okay, cool. For this specifically, this is an SN2 reaction. So all we do is come here, we kick this off. Cool? Cool. We come here, we kick this off. All right. Forming an enolate ion. Okay. The amount of enolate ion depends on two things, the pKa of the carbonyl compound and the strength of the base that's used. This is not going to work, right? Because we have an HO minus. This pKa of the H2O is 15.7. This is 17. So the reactant side would be favored. And let's see, 17 minus 15.7. Okay, so Henderson-Hasselbalch says that you'd approximately have 5% of the compound, I think, in this form. So we get about 5% of the reaction that we're looking for, which is not nothing, but it's pretty bad of a yield, right? So we use LDA. LDA gets you about 100% because it's a pK of 35 versus 17. Henderson-Hasselbalch that you could see how that would be the case. LDA is just a really strong base. DIA, like it's just LDA but with a proton, right? I don't know if you're really on the hook for LDA's structure, but amide and dipropyl, propyl, lithium, Li plus, N minus. Cool. Alkylating the alpha carbon. So again, we talked about why this doesn't work. Okay, it is about 5%, so that's pretty close. Right? Because of acid-base chemistry, we say that we favor this product over this product. With this product, again, always show it in this enolate ion form. Never show it as a minus here. This, again, like when you're predicting products, it's okay. But if you're drawing out this mechanism, please show it like this. Okay, alkylating esters, aldehydes, nitriles. So it's exactly what you expect. These reagents will remove the most acidic hydrogen. And in this case, here we have resonance here and here. Here we have resonance goes here, kicks this up. Here, resonance withdrawing group. Here, resonance both ways. Cool. Okay, so I want you to consider this question. Okay, so pause the video after I talk about this. When we're alkylating asymmetric ketones, which side do we deprotonate? So I'll give you a hint in a second, but if you want to try without a hint, pause the video. Okay. So LDA goes through a carbanion mechanism, right? And we remember our trend for carbanions is minus on the species that we deprotonate from, right? But we also note that this product at the end is more stable. Interesting. So how do we know which one? Okay, so this is a kinetic versus thermodynamic consideration. So a kinetic product basically is something that forms faster. So in a reaction energy diagram, right, we have the first hump that corresponds with activation energy. So the lower that this hump is, it's a correspondence with the kinetics of it, okay? So if this hump is lower, that means it's a kinetic thing. So if we don't have enough energy, and I'll talk about how you know if we don't have enough energy later on, we'll form the kinetic product because the transition state is more stable. Okay, a carbanion is more stable on this spot than it is on this spot, right? So it's gonna be more stable for HA for specifically kinetic enolates. LDA minus 78 degrees Celsius. We form the kinetic enolate, the less stable one, in the long run. If we're given enough energy, if we see LDA 0 degrees, that means we're going to form the thermodynamic enolate. Even though it goes through a mechanism that starts with a carbanion that's less stable, the ultimate end product is more stable. And we say that if we have enough energy, thermodynamic product is at the end of the day the difference between the starting reagent and the ending reagent, right? So even if we go through a higher activation energy, our result is a more stable compound. And if we have enough energy to do that, we will. Okay, cool. Alkylating and acylating the alpha carbon using enamines. So enamines are something known as a soft nucleophile. So we'll talk more in depth about what a soft nucleophile is, but just as a quick thing, the easiest way to recognize it is we have to have two arrows, right? So remember when we have an alkene, the alkene can directly attack the electrophile, right? But in this case, the alkene's conjugation with the nitrogen is such that we actually have to bring this lone pair down before we can attack the E. So it's two arrows here. So strong nucleophile would have just needed, one arrow. So that's a quick way to tell, right? So soft nucleophiles also prefer soft electrophilic spots. And again, we'll talk a little bit about why that is later on. Okay. Acylation reaction. This is an example. Comes down, kicks here, tetrahedral intermediate comes down, kicks out. Cool. HCl, um, it reduces this to a carbonyl. It's exactly what you would expect, right? We install the OH and we do a bunch of protonation, deprotonation steps to remove the stuff here. Cool. It's just a hydrolysis, right? We learned that we can reverse imines with HCl, H2O. And also, this is a formal charge of plus, right? So it's already kind of unstable. Cool. Okay. Alkylating the beta carbon. So using enamine as a nucleophile, we attack at the three position. So well, okay, we attack. This is an example of 1, 4. So in reality, 1, 2, 3, 4. We attack here as opposed to here because a soft electrophile prefers a soft nucleophile prefers a soft electrophile, right? And again, soft electrophile just means that we have a lot more arrows. So in reality, what happens is this comes down, this attacks here or sorry, these Nolan pairs come down, and then we attack here, and we have to have a bunch of resonance and electron movement, to get this attachment going, right? So once we attach here, one step, two steps, as opposed to if we just attached at the electrophile, once we attach, it's just one step, right? So more arrows, more electron flow, takes longer, soft versus hard, right? Soft has to kind of be pushed in the right direction, right? Okay, cool. So with that, we'll get a tautomerization after. H2O, HCl, we'll remove this. Cool. Dicarbonyl. Michael reactions using other enolates. Okay. So again, nothing we haven't seen here. In reality, this is again, for predicted products, it's okay, but you want to draw it as an enolate ion. So the double bond here, minus here, then comes down, grabs this, this moves, this kicks up. Cool. Tautomerization. Perfect. Okay. Acylation of the alpha carbon. So we just talked about. Okay. Aldol addition reaction. So the first aldol additions that we're going to talk about are when we have two equivalents of the same compound. Okay. We're going to form something called a beta hydroxyaldehyde. So the way you predict this is pretty easy. You kind of just take this and you glue it to another one of these. So you see this is similar to this, except at the hydrogen. And we see 1, 2, 3, 1, 2, 3, OH. Cool. Okay. It's not that bad. Um, all right, beta hydroxyketone. So an aldol condensation reaction. What exactly is happening? It goes through this mechanism called E1CB, right? Um, so let's take a look at it. So HO minus will attack here, kicks this up. Then these electrons come down. This double bond moves from here to here, and we remove the water, and we're left with a conjugated carbonyl, right? So make sure to draw the electron transfer in this way. Do not draw it like this. Um, the reason why we don't draw it like this is because sometimes in organic chemistry, when we're trying to go from one compound to another, we have to take smaller steps, right? Like we can't jump too much. Um, and the way that this reaction is, it's such that the energy gap between these and these is too dramatic. So we have to go through this intermediate and then go to here. So another thing to note is make sure that there are alpha hydrogens that can be picked off for E1CB condensation to occur. So if we didn't have alpha hydrogens, we can't do an elimination, right? And just a quick thing here, like remember, like draw the resonance patterns and arrow patterns like this. You might be tempted to be like, oh, this here goes like this and this eliminates because you get the same final product, but it's not exactly the correct mechanism. So again, it's one of the cases of for predict the product, you won't really have an issue, but if you get to draw out the mechanism, there will be an issue. Okay. And then for this, heat is not required when you have a conjugated system, right? So whenever you have something aromatic, whenever you have something benzoic, allylic, okay. Increased stability due to the extended conjugation can lead to the condensation reaction without any heat, right? So again, resonance and aromaticity, benzoic, allylic, saving the day. Okay, crossed aldol reactions. So we just talked about an aldol reaction when we have two of the same molecule, right? Two aldols. So cross reaction is when you have two different carbonyl compounds and they're used to form a mixture of four products, right? Well, they're not used to form a mixture of four products. They form four products, right? Two times two is four. right? So if I have one product here, one, two, three, four. Okay, so there are ways to control this and only get one product. The first way is to use a carbonyl compound with no alpha hydrogens. This compound has no alpha hydrogens. This is not an alpha hydrogen. Again, this is attached ipso. This is attached directly to the carbonyl O. So when we do this, we have one alpha hydrogen here. This is the thing that has alpha hydrogens. We're adding this slowly to make sure that this reagent is in excess. Okay, so that's what add slowly means. So we'll get this as our final product. Okay, and again, it's good to understand these, but generally speaking, as long as you can predict the product, it's not that bad. What will happen is we'll basically take this and we'll glue this here, and instead of the H, this O will go away. This will become a double bond, and we'll just glue it right here. Okay, so take a moment to see how that is. Cool. Okay, if we have alpha hydrogens on both the compounds, we can use LDA for selectivity. Okay, so LDA, we add this slowly. Again, we're keeping one in excess. This will be the only product. Okay, this is a quick predict the product of the following reaction. I don't know, you can pause here if you want, but I think that it's relatively straightforward. Cool. Crossed aldols, four products. This is how you get the four products. One here, add, right? Okay, Claisen condensation. So this is an aldol addition reaction of esters. So it's pretty much the exact same thing, except now there is an ester, as opposed to before it was not an ester, right? So the mode of reactivity will be rather similar, but it's a little bit different. And so let's pay attention to the arrow pushing. So basic conditions, will deprotonate right away, comes here, kicks up, comes down, grabs this, kicks up, attacks here, leaving group, right? So we actually have a good leaving group here. So that's why we get a dicarbonyl here, as opposed to last time we saw a carbonyl and a double bond. Okay. And then note that this something will keep on happening, right? So we kind of stopped after like one enolate was formed here. We could actually form a second enolate here because this point here is resonance stabilized both ways, right? So it's really, really good. pK of 10. So it actually will keep going. Um, so we'll end up with this compound. And again, you might think like, oh, this is literally the same thing as this. So it is. And this is because of the fact that we used a conjugate base of the ester segment. These are the same thing. If they weren't, then it's likely that we would get a mix of products, which is why you use the conjugate base. Okay, again, it's one of those things which just like you can predict the product properly, but kind of like mechanistically, you want to make sure you think about it in this way. We must deprotonate the beta ketoester for the reaction to work. So the ester must have at least two alpha hydrogens, right? So we have a deprotonation here, and at the same position, we have another deprotonation. So we had three alpha hydrogens on this position, but you need at least two. This will not work. This only has one alpha hydrogen, which means that there's no alpha hydrogen here to deprotonate, so the equilibrium will actually favor the reactants, right? So if we just got this, you might be like, oh, this isn't a problem. Why is this a problem? It's because this will be favored. Okay. Cross-Claisen condensation reactions. These limitations are the exact same as the aldol reactions. Multiple products. So if you want to control Claisen, use one ester with no alpha hydrogens. Add slowly. Again, the add slowly, all that is saying that we want this to be in excess the whole time. This happens a lot in polymerizations if you ever are interested in synthetic chemistry. We have a certain feed ratio of one compound, and based on that, we can have a more predictable product. Either that or you form the enolate first using LDA. Other cross condensations. So I'm not going to talk too much about this, but I'll leave it to you to take a look at these. They're effectively the exact same thing as the previous ones. They're just, other cross condensations. Okay. Always add the compound with the alpha hydrogen slowly so the other is kept in excess. Cool. Acid workup can be pretty much any acid. It's not that deep. If both the ketone and the ester have alpha hydrogens, use LDA. Exactly what we saw before. The two ways to make sure that we have one product are the exact same for every single cross condensation we do. Well, with some caveats, but not for the purposes of this class. Okay, intramolecular reactions, Dykman condensation reaction, and intramolecular Claisen condensation. Okay, Mostly all of the intermolecular reactions we do are the exact same mechanisms as the intermolecular. The only difference is the two functional groups that are reacting just happen to be connected on the same molecule, and the distance between them is enough carbon such that we get a favorable ring formation, right? So we have a tendency to form 5 or 6 membered rings. Well, we generally never form for in these specific reactions a 3, 4, 7 membered ring. Okay. So again, it's exactly what you expect. We don't form with this product, although it might seem plausible at first to get an enolate ion here or here. That's because we'd form a 3 membered ring, which is really, really bad, very bad ring strain. So this is the only product. Okay, predicting the products. So again, make sure that you're really good at predicting the products and you can do so pretty quickly without having to go through the mechanism. So count the carbons: 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. One of the carbonyls will stay. The other one will become a tertiary alcohol. Tertiary alcohol. Carbonyl stays. Tertiary alcohol. Carbonyl stays. These, this tertiary alcohol, this carbon that's connected to this alcohol has to be 1 carbon away from the carbonyl, right? So carbonyl, alpha position, beta position. Carbonyl, alpha position, beta position. Carbonyl, alpha position, or sorry, alpha position, beta position. Nothing new. Okay. Robinson annulation. So this is one that has a little bit of complexity associated with the mechanism. And again, like it's one of those things where you should know how to predict, understand the mechanism, but I think it's sufficient if you, know how to predict the products. So this is a mix between Michael and intramolecular aldol. So basically this all this is saying is recall like a phosphoylide. You remember like how like the bond would kind of move around to make a 4 membered ring. This is exactly what's happening. So this is attaching to here, this is attaching to here, and when we attach here, double bond, single bond. Cool. It's pretty easy to predict, right? So we just line this up. We make sure that this carbonyl is, alpha, beta, not really, but like it's lined up. We have these parallel to this. This is parallel to this. And this is our product, right? We can split it here to predict the initial reagents. Okay. I would pause here or like cover up the, you know, reactants. But anyway, you should be able to go back and forth between these. You should be able to predict products from reactants, reactants from products. Okay. And you draw this V thing. This V thing will always be drawn as such, right? So the V will be pointing to a carbonyl. This V is pointing to a carbonyl. Cool, cool. And it'll always be the carbonyl, ketone carbonyl. It'll always be a ketone carbonyl, I believe. Okay, decarboxylations. So decarboxylations are very favorable when they're beta. When they're beta, you only need heat, okay? Because what happens is this O minus, basic conditions, we attach here, we could kick this off. Cool. That's it. When we have a hydrogen here, it's slightly different. We get something called an intramolecular proton transfer. We get this like cyclic thing going on. That's because we have proton, hydrogen, hydrogen, or like hydrogen bonding here. So that's why this is more stable. Like that's why we get this turn, right? And we form, pretty much the same product, except this is neutral, this is minus. Makes sense, right? Because we started with minus, we go to a minus. We start with a neutral, we go to neutral. This also works with dicarboxylic acids. And with that, like you just end with the carboxylic acid, right? So predict the products you cut here. This is what you ended with, right? Predict the products you cut here. This is what you ended with. Predict the products cut here. This is what you ended with. Cool. Which of the following would decarboxylate when heated? So we need a beta carbonyl for decarboxylation, right? So alpha, this is not beta. This is at the alpha position. We will not undergo decarboxylation because here there's not a way to resonate the electrons such that we can have something favorable. Alpha, beta, this is okay. Alpha, beta, this is okay. Alpha, beta, gamma, this is not okay. Okay. Malonic ester synthesis. So this is a little bit misleading because, we don't actually synthesize an ester. We're just using it as a starting reagent. But anyway, it's a combination of alkylation at the alpha carbon and decarboxylation. Um, so it's pretty easy to predict the final structure. Again, it's good to be knowing the mechanism too. And it's important to note here that this is actually able to be deprotonated again. So we could use another equivalent of ETO minus and add install another R group. Or if we had an RBR, if we had a di brominated R, like if we had a BR like coming out of this, we can form a ring. Because, like I said, like once we deprotonate it here, we can do another RBR. And if the BR happens to be on this molecule again, we'll form a ring. Hydrolysis, OH, we swing around because we get stabilization associated with hydrogen bonding. We get this little circular thing. We go here, we kick this off, we come up, we get this compound. Um, Okay, cool. So synthesis via malonic ester, this is a quick practice question that you could do. Especially planning practice on that final practice sheet. Okay, malonic ester synthesis. We just talked about this. Acetoacetic ester synthesis. So it's the exact same thing, except this group, instead of being an OET, is going to be just a methyl. I'm not even going to go through the mechanism because it's, pretty much the same thing. And we'll end with this compound. So, it's exactly what we ended with that, but instead of having a OH at the end here, we have an R right here, right? We install an R, right? Because this is what we start with. Cool. Okay, it's also important to note that this part of this mechanism is SN2, so it's privy to all the limitations of SN2. We cannot use a tertiary bromide. It will not undergo SN2 because it is tertiary. Tertiary alkyl halides do not undergo SN2 reactions. Okay. So that about wraps it up for reactions at the alpha carbon. Um, so this does conclude the content for your test. Yeah.